So, welcome back to this later half of today's lecture. So, we have seen how to produce concrete maximal ideals in the polynomial algebra. We will use this to construct also maximal ideals which are not of this type. So let me write again what we have proved. What we were looking for, this set of maximal ideals SPM K x1 to xn, and remember that K is a field, and we have K in here, and we have home K algebras polynomial ring Kx1 to xn, values are in K. This we have checked that this is an isomorphism, right? Not isomorphism, this is a bijective map. So, A1 to An, this is going to that epsilon A. This is the algebra homomorphism from the polynomial ring Kx1 to xn into A. And then we have, what we have checked is the kernel of this homomorphism, that is the kernel of epsilon A. This is a maximal ideal, that is what we have checked. And also we have proved that this kernel is generated by these polynomials x1 minus a1, xn minus an. So, this is also this I also want to denote by m suffix a. Now, one might think that all maximal ideals are like this. So, first of all, let us see some examples, so that there are other maximal ideals which are not like this. So, one example let us see. Let us take K equal to R, and let us look at the ideal generated by x square plus 1. I am taking only n equal to 1. Well, we have checked that this is a proper ideal in Rx, and then whether it is maximal or not, we have to check whether the quotient residue class ring is a field or not. So, what is the residue class ring in this case? Rx mod x square plus 1. This is isomorphic to C as R algebras. In fact, you can give the isomorphism. In fact, you can define a map from Rx to C by our universal property of the polynomial ring, that I will send capital X to I, imaginary unit. Once it goes to I, this polynomial is in the kernel. So, this polynomial x square plus 1, this is epsilon suffix I, it belongs to kernel of epsilon suffix I. But now use the division algorithm to check that this polynomial generates it. This is a monic polynomial, and if you take anybody else in the kernel f, what do? This is a real polynomial, and divide by this monic polynomial. You can always divide. So, and write it q times x square plus 1 plus a linear term will come, and that will not. So, linear term will look like ax plus b, and this will never become, a and b are real numbers because we are applying division algorithm on this ring. So, A, B are real numbers, and then when you plug it in x equal to I, it becomes 0, f of I is 0, because f is in the kernel here, we have started with, this is 0, this is already 0, so f of I is equal to AI plus B. But then I will, you can, then that will imply I is a real number, which is not true, contradiction. Either contradiction or say that, so because I is, let me rub this, so that should imply A equal to B equal to 0, because 1 and I is linearly independent. I would like to use linear algebra as much as possible rather than giving complicated arguments. So, therefore, we have proved that the kernel is generated by this polynomial x square plus 1, therefore, C is isomorphic to this. Therefore, this actually is a maximal ideal. So, this proves that the ideal generated by x square plus 1 is belongs to SPM Rx, and this is not of that type. So, therefore, this in general, this set properly contained. These are not all maximal ideals in general. For example, I can give many more if you give me, if I take field k equal to q. If I take k equal to q, what do I do? You see, now the problem will shift to somewhere else. And suppose I have fx belong to qx. Suppose I have irreducible polynomial, irreducible, and let us also monic polynomial. Irreducible means it does not factor into two proper factors, two non-constant factors, because constants in this case are the units. We have checked, let me remind you, we have checked, or at least I have mentioned that units in this polynomial ring over a field q is q cross. So, the only unit polynomials are the non-zero constant rational numbers. So, if I take any irreducible monic polynomial, that will not be constant, and there are many as such. You would have seen, So, can you list some of the irreducible polynomials over q? You can list many. For example, if I take x power n minus, let me write first smaller n's, x square minus 2, this is irreducible, or x square minus 3, or x square minus pq, or y 2 prime numbers, x square minus p1 to pr, this is square free. All these polynomials are irreducible and they are monic. Or, and if I want degree n, well, degree n also you can write x power n minus p1 to pr, these are all irreducible polynomials. So, this immediately follows from what is known as, I will write in this side, Eisenstein criterion, Eisenstein's irreducibility criterion for polynomial f inside qx, let us say. I hope you remember this. If you do not remember, you can learn, or I will write in exercises. Alright, so let me rub all this. So, you start with any irreducible monic polynomial, and this irreducible plus monic I keep calling prime polynomials. Alright, so and of degree bigger or equal to 2, and we have seen there are many n. In fact, given any integer n, given any natural number n, there are lots of prime polynomials of degree n. Okay, so now I claim that ideal generated by Fx is a maximal ideal. In Qx. So, what do we have to prove? So, first of all, what does our residue class ring is? Qx mod Fx. This is our residue class ring, and we definitely know this is an integral domain. This is integral domain, because that is a prime polynomial. And so, prime polynomial means that if a product is divisible by this f, then at least one of them is divisible by f. But this, when you translate, that will become a prime ideal. So, this is degree 2 bigger equal to 2, therefore, it cannot be unit, and therefore, this ideal is prime, but then that is equivalent to saying the residue class ring is a integral domain. Okay, it is an integral domain and it is a monic polynomial. So, I claim that this is also finite dimensional Q vector space. It is a vector space also. This is a Q algebra. This is a residue class of a Q algebra, polynomial algebra. So, this is a residue class algebra. So, this is also Q algebra. And it is finite dimensional Q vector space. In fact, not only Q vector space, but it is finite dimensional actually. And what is, how do you check that? In fact, finite dimensional Q vector space of dimension equal to degree of this polynomial Fx. How do you prove this? So, see you have a map here. This is a residue class map Qx to this, and f we have written like this. F of x is a monic polynomial. So, let me write f of x as x power, let call this degree to be n, x power n plus a1 x power n minus 1 plus a n, where a1 to a n they are elements in Q. When you go mod, and let us write where do these x go. This I want to write image of x, capital X. The image is small x. This is a surjective map. Image x, capital X go to. So, this is in, if you are in a lower kg or upper kg, then this capital X is in fact capital X, small x is in fact coset of capital X, this is how we will write the cosets. This is abelian group. So, you write cosets like that, but you see how complicated it is. So, we assume that we have gone to bigger class and then we do not write like this. So, small x, and once I know where capital X goes, I know where all polynomials go. So, therefore, where will the polynomial f will go? Where will capital this polynomial fx will go? I have to evaluate that f at the small x, but then it is in 0 it is. So, this is 0. So, that means what? So, that means, so 0 equal to f of small x, that means x power small x power n plus a1 small x power n minus 1 plus a n, this is 0. That means this is equivalent to saying x power n belongs to the sub algebra generated by X. So, these belong to Qx. So, let me write more explicitly. This means image of this epsilon evaluated X map is generated by 1 x power n minus 1 as a Q vector space, because any element will be a polynomial and you divide that polynomial by this f and then you get a lower degree polynomial. So, image is generated by this. So, that means we have proved that. And what is image of epsilon x? Image of epsilon x is nothing but Qx, Q small x, which is Qx mod ideal generated by Fx, capital X. And this is a generating set for this vector space, and also it is linearly independent because of the, you can always, if some combination of these guys there is a linear dependence relation equal to 0, then that polynomial will be divisible by that f, but f has a bigger degree than n minus 1, therefore it is 0. So, in fact this is a Q basis, in fact a Q basis. So, we have proved that this is a finite dimensional Q vector space, this is finite dimensional Q algebra. So, then what do you wanted to prove? Now, I want to give you a lemma, because this I want to use it multiple times. So, K any field, let K be any field, and let B be a K algebra which is an integral domain if B is finite dimensional over K, then B is a field. We will prove this, but that will finish our problem, because what we wanted to prove, we wanted to prove this residue class ring is a field, because we wanted to prove this is a maximal ideal. But to prove it is, and we already know it is an integral domain, that we already know, we have just checked, and we also know it is finite dimensional. Therefore, so by lemma it follows that Qx modulo Fx is a field, and hence ideal generated by Fx is a maximal ideal in the polynomial ring over Q in this. And how many such? As many as prime polynomial definitely, and there are so many we saw. So, therefore, whatever we listed, those maximal ideals corresponding to the points, there are many more outside that also. Alright, so let us prove this lemma. So, proof of lemma, very simple. What do we want to prove? We want to that B is a field we want to prove. So, let 0 not equal to B in B. To prove B is a field, I have to check that every non-zero element has the inverse in B. So, to prove that B has multiplicative inverse, in B, that is what we want to prove. All right. So, let us look at the map for this. Look at the map lambda times A, lambda suffix B, which is a map from B to B. Any C goes to B times C, left multiplication by B, this is a map, and B was what? B was a K algebra. So, this map is, I say this map, it is clear that this lambda map is K linear. So, what do we have to check? Those precisely will be, what will be useful is precisely for the axioms of K algebra. So, for example, I have to check this lambda B of C plus C prime equal to lambda B C plus lambda B C prime. This is what we want to check. Let us see, convert it. This is by definition what? This is B times C plus C prime, and this is by definition, this is BC, this is by definition plus BC prime, and we want to check this. But that is the axiom that the plus is compatible with the scalar multiplication. So, this is additivity, and now K linearity. If I have some A in K, what is lambda B of AC, and we would like this to be equal to what? A times lambda B of C. Well, what is this by definition? This is B times AC. But B is, I will think B as 1 times B. So, this is a scalar in K, this is a scalar in K, and these are two elements in B, and the compatibility of the multiplication and scalar multiplication says that this is same as, I can take this A with 1. So, 1 times A times B times C, which is this, which is A 1 times A is because 1 is a multiplicative identity in the field K. So, this is A times BC, but this is same thing as this. So, therefore, the algebra B is a K algebra, the axioms of K algebra checks that this lambda map is a K linear map, and by our assumption given, this B is a finite dimensional K vector space. Okay. Now, further note that lambda B is injective, and of course, we have noted that it is K linear. Why is it injective? Because it is an integral domain. If C and C prime both in B, if lambda B of C equal to lambda B of C prime, what does this mean? This is BC and this is BC prime, which is equivalent to saying B times C minus C prime is 0, but B is not 0. Therefore, C minus C prime is 0, which is equivalent to saying C equal to C prime. So, therefore, this is an injective K linear map of the same vector space, finite dimensional. Therefore, it is an automorphism. So, because for a finite dimensional injective, surjective and automorphism, they are all equivalent. So, by linear algebra, since B is finite dimensional, lambda A is bijective. But that means everybody is in the image of lambda A, lambda B, I called it B. In particular, one belongs to the image of lambda B, that is 1 equal to lambda B of C for some C in B, but that is, this is same thing as saying 1 equal to BC. So, I produce actually the inverse of B. So, C is equal to B inverse exists. So, that proves the lemma, and that proves we produce many maximal ideals in the polynomial ring over Qx. Now, same thing you can do it for finite field. F is a finite field with finitely many elements, then SPM F one variable x. This of course contains all this x minus a, where a is in F. All these are maximal ideals here, but we had many more, and here also there will be many, because over a finite field you can find many polynomials which are prime. Over a finite field there are many polynomials which are prime. So, let me write a statement. So, let us write it as a lemma. There exist, in fact infinitely many, there exist infinitely many prime polynomials in Fx of degree bigger equal to 2. Degree equal to 1, there are only finitely many, they are all these linear polynomials, linear monic polynomials. And how do you prove this? Proof. Suppose they are finitely many. Let me call them pi 1 to pi r, pi 1 to pi r in Fx if are all prime polynomials in Fx. This is a very famous proof. This is called Euclid's proof. Euclid proved it for numbers, but the same trick works for the polynomials over a field. Then consider the new polynomial 1 plus pi 1 to pi r. This is a polynomial in Fx, also monic, and also degree bigger equal to 2, because we have taken, if they are finitely many, then there are few are these linear ones and other may be, but any case there are at least 2 linear factors. So, this polynomial is of degree bigger equal to 2. And now look at the factorization of this polynomial. We know that polynomials over a field can be factorized into irreducible factors. So, there will be at least one irreducible factor. This is not a unit element. So, there is at least an irreducible factor, and that will correspond to a prime polynomial, and that prime polynomial have to be different from this pi 1 to pi r, because that prime factor pi. So, let I would say just then every prime factor of pi 1 to this not of 1 plus pi 1 to pi r is different from all pi 1 to pi r, because it is a factor of this, it cannot be equal to this. Then if it is equal to one of them, then it will also divide 1, which is not possible. So, therefore, what we approved is in the polynomial ring or a finite field, there are infinitely many polynomials which are prime, and each one of them will give you the maximal ideal, and all these maximal ideals only finitely many as the cardinality of the field, they are those linear, the given by the points, and the remaining ones are non points. So, therefore, now this also suggests that the field will play a very important role in algebraic geometry. So, R, Q and finite field will be the worst cases. R is little bit better because the only irreducible polynomial is of degree 2, or in note that. So, I just want to note this for future use. In Rx, what are the prime polynomials? Prime polynomials are obviously the linear ones first, x minus a is in R. There are also uncountably many. And now the quadratic ones. So, x square plus px plus q, where b squared minus 4q should be negative, p square less than 4q. These are obviously irreducible, because if at all it factors, then the zeros of this polynomial will be real numbers. But then the discriminant, this is school what you studied. Alright, so these are all, because if you have a cubic polynomial, it has a real 0, and therefore it will not be prime, it will factor. So, these are maximal ideals and these are maximal ideals, because I know all ideals are principal in Rx. So, therefore, SPM Rx is precisely equal to this. Our notation was MA, A in R, union. If you can identify this, maybe you can identify these with, or keep it the same, x square plus px plus q, where p square is less than 4q, pq are real numbers. These are all maximal ideals. So, we have described the maximal spectrum for the polynomial ring over R in one variable, and over Q it is much more complicated. You see, it is not just these two, any degree there will be several. For finite field also similar thing, but for C, SPM CX, I will prove this is equal to in fact only this MA, A varies in C. That means these are precisely the ideal generated by these linear ones, x minus A in C. So, in other words, we can identify this with C. A to MA. This is the identification. And this is not only true for one variable, but we will prove this for many variables, finitely many variables, and that is precisely one form of Hilbert's-Null-Stern-Zatz. So, this is a very particular case of Hilbert's-Null-Stern-Zatz. This is the cornerstone, this is the bridge between algebra and geometry. This I will show you in the coming few lectures, many one. So, with this I would stop this lecture and we will continue this. So, you might have realized that we have to study polynomials over fields, finitely many variables, and ideals in that, maximal ideals in that, prime ideals in that, and so on. So, this is what we will specialize. For that I will need some algebraic statement. Now and then I will switch to algebra. Okay. So, I will stop here. Thank you.